And I forgot I was supposed to be recording, so I just started recording. Okay. So 3 plus -1 is 2. All right, so addition is pretty simple. It's also good to be able to visualize what's happening with vector addition. So I'm also going to draw a picture of that just so we can see. So here I'm going to draw the vector 1, 3. So that's my vector u. If I draw the vector 3, -1, so down here like that, that would be my vector v. And notice that there's some, which we've already computed, was the vector 4, 2. So let me draw that as well. So it'd be about here. Okay. Okay, so that was u plus v with coordinates 4 and 2. So if I do my picture well, you should notice that u plus v forms the diagonal of this parallelogram with edges u and v. So that's one way that you can visualize vector addition. There's some u plus v is the diagonal of the parallelogram. With edges u and v. Another way that you can think of vector addition is if I take the vector v and I draw it starting at the end of u, you can think of u plus v as forming the third edge of the triangle, formed by u and v, like that, okay? So more precisely, if you attach the head of v, or if you attach the tail of v to the head of u, then there's some u plus v will be the vector connecting from the tail of u to the head of v, okay? All right, so just moving on, I'll quickly address scalar multiplication, which is also fairly simple. Well, okay, so scalar multiplication. And again, it's pretty simple, so just a quick example will do, I think. So let's draw a vector in R2. Let's look at the vector 2, 4. Now to multiply a vector by a scalar, all you do is multiply that scalar into the components. So multiplying u by 2, it's going to multiply each component by 2. So I will get 4 and 8. If you were to plot the vector 2u in the picture, you would find that 2u points in the same direction as you, but it's twice the length. Okay. So visually, when you multiply a vector by 2, it doubles in length. Likewise, if I want to multiply by, say, a half, so half of u would be the vector 1, 2. And if you draw the vector 1, 2 in the picture, it's half the length of u. So that's important to keep that picture in mind. When you multiply a vector by a scalar, it scales the length of that vector by that amount. And then finally, if you multiply by a negative scalar, so let's just look at negative u. So multiplying each component by -1, it would just be -2, -4. And if you plot -2, -4 in the picture, negative u will have the same length as u. But since you multiply by negative, what happens is that flips the direction. So now it points in the opposite direction instead. All right. Okay, so then after talking about addition and scalar multiplication, let's just talk a little bit about linear combinations. So I'm going to define what a linear combination is first. So a linear combination of vectors, let's say v1, v2. Let's say you have some number of vectors. Let's do vn. Okay. All right, so if you have n vectors, a linear combination of them is any vector of the form c1 v1 plus c2 v2 plus so forth up to cn vn, where c1 through cn are all scalars. Okay. All right, so then just as a very simple example, if I have two vectors, let's say 1, 3, and -2, 2. So if I do, say, 2u minus v, then this would be a linear combination of the vectors u and v. And if I just do the arithmetic real quick, 2u is 2, 6. So then when I minus v, that's going to be 2 plus 2 is 4, and 6 minus 2 is also 4. Okay. So then you could say this vector 4, 4 is a linear combination of the vectors u and v. Okay. All right, so now let's move on. And again, if you guys have a question, let me know and post it in the chat. Okay. So I'm going to talk a little bit more about linear combinations now. So to start with, I'm going to draw two vectors, u and v. And then I'm going to form a parallelogram with my two vectors. And we just discussed with vector addition how their sum, u plus v, forms the diagonal of this parallelogram. Now, u plus v is a linear combination of u and v. So specifically, it's 1u plus 1v. So that's one linear combination of u and v. Now, instead of looking at the diagonal of the parallelogram, I'm going to pick another vector, one that lies inside of the parallelogram. So I've got this new vector that I'm drawing in red, which I'll call w. And so my question is, how is this vector w related to the vectors u and v? All right, so I'm going to zoom in to make the picture a bit bigger. All right, so what I'm going to do in my picture right now is I'm going to form a smaller parallelogram using the vector w. All right, so this red parallelogram that I've drawn here, its sides are parallel to u and v. So if I draw this vector down here, and then this vector up here on the left, notice that this vector here, it is a scalar multiple of u. So I'm going to call that cu for some scalar c. And likewise, this vector here, we recognize it as being a scalar multiple of v. So that red vector is maybe dv for some scalar d. And then because w is the diagonal of the parallelogram formed by these two vectors, we can reason that w is equal to cu plus dv, which in particular tells us that w is a linear combination of v and u. Okay. All right. Again, if you guys have any questions, just post it in the chat. If something that I'm saying isn't clear to you, you can ask and I can try to clarify. Okay. Now, in this picture, we can say a little bit more. So we said this vector was some scalar multiple of u. Because it points in the same direction as u, we can say that C was a positive scalar. And because it is shorter in length than u, we can also say that C was a scalar specifically between 0 and 1. Using the same reasoning, you can also conclude in this picture that D is also a scalar between 0 and 1, because it points in this, dV points in the same direction as V, but it has a shorter length. All right. Now, if I draw any other vector inside of this parallelogram, you can make a similar conclusion. So any vector in this parallelogram is going to be a linear combination of u and v, where the scalars, the coefficients of u and v, are between 0 and 1. And we can conclude that the set of all linear combinations of these vectors u and v with coefficients between 0 and 1 all right, so this set of all linear combinations would be visually represented by the parallelogram formed by u and v. Okay. All right, so next, let's take a look and see what happens if we adjust the range of the coefficients so that they are not restricted to be between 0 and 1. So let's imagine what if we had C being between, say, 0 and 2 as an example. And maybe let's say D, if we restrict D to be between 1 and 3. Let's think visually, what would the set of all of these linear combinations look like? So what do these linear combinations look like? Okay, so I'm going to draw a picture of that. Okay, so we had U looking something like this, and V looking something like this. So if C and D are between 0 and 1, that places us inside of this parallelogram. Now, if I allow C to go up to 2, So when c is equal to 2 and we would have 2u, we know that 2u is going to bring us all the way out to here. So 2u is twice the length of u. And then d, if we allow d to go up to 3, then we know 3v would be 3 times the length of v. So it will stretch all the way to about up to here. Okay, if you imagine that is 3 times the length of v. So now I'm going to form another parallelogram with 2u and 3v. All right, so let's see here. That's 1u, that's 1v, and then this was 2v. Okay. So if I need to be between 0u and 2u, but also between 1v and 3v, that's going to place me inside of this region here, okay? So it has to be between all right. It has to be between 1v and 3v, which is why it's in this range and doesn't include anything down here. And then since z is between 0 and 2, it should start from 0u, which was here, and stretch out to 2u, which is here. So that forms this region like that, okay? And then just similarly, if I look at just this little parallelogram, this little parallelogram would be where c is between 1 and 2, but d is between 0 and 1. As another example, if I just look at, say, this parallelogram up here, so this is where c would be between 1 and 2, and d would be between 1 and 2 as well. Okay, so I'm going to see what that question was. So the region that I shaded in was c between 0 and 2, and d between 1 and 3. Like that, okay? All right. Now you can do something similar, so I won't take us long, but let's do one more example. Let's do one where one of the coefficients is negative. So let's just take a look real quick at cu plus dv. But this time, let's say that maybe, let's keep c between 1 and 2 this time, and let's maybe put d between -2 and 0. All right, great. So I'll also draw a quick picture of this one. So I'll start with my vectors u and v, which looks something like this. I should move my u. All right. So right now that's at 1v and 1u. So with c between 1 and 2, I need to go out to a distance of 2 u's, so that's up to here. And because d is negative, when you multiply v by a negative number, remember that reverses the direction. So negative 1v would be here, the same length as b, but in the opposite direction. And then negative 2v would be up to here. Okay, let me take a look at those questions. Oh, that's a good one. Okay. Yeah, component form, I think Lexi is correct. Component form is usually just asking for like the coordinates, like the xy or xyz coordinates. You could write it, I think, in both forms I introduced earlier, xyz. They would probably also accept it as a column. Even if they haven't introduced that yet, I think they would probably accept that as an answer. That's another way of writing this out. Actually, let me finish my example and then let me talk about that real quickly as well, okay, Joshua? That's maybe somewhat related to what I'm talking about, so I'll go ahead and mention that as well. All right, but let's finish up this example real quickly. So here I had c is between 1 and 2. So that puts me somewhere in this range. And then with d being between 0 and negative 2 down here, that would correspond to this parallelogram in the middle. So c is between 1 and 2, and d is between negative 2 and 0. And I know someone asked so quickly if I did want, let's say if it were just c less than 1, let's maybe say d is between, let's say maybe d is greater than 3. Let's see what that will look like. All right, so I'll draw again uv real quickly. Okay, so this is already where c is equal to 1. So c less than 1 is going to be to the left of that line. Now d affects v. So if I think about 3v to start with, v is about here. And if it's d greater than 3, that would correspond to everything above this line. So it's above 3v and to the left of 1u. So it's going to be sort of an infinite area up here. Regarding that, so equals would have to include the edge, and if it were just strictly greater than, then it would not include the edge. So as an example, for the example I just did, it would not include this edge, and it would not include this edge. If you want to include the edge in the drawing, probably a solid line rather than the dashed lines that I've been doing. would be a good way to indicate it. Didn't quite pay attention to my earlier examples about that. Let's see, like for these ones up here, you would want to include the edge since it was less than or equal to everywhere. Okay. All right, great. And finally, if I consider all possible linear combinations of the vectors u and v, so all possible linear combinations means there's no restriction on C or D. So they could be any number, any real number. So what would this look like? Any guesses? Yep, in this case, yeah, in this particular case, that's good. It would be an infinite plane. So I don't know how you would necessarily draw that, but you know, it's everything, the entire sheet of paper. Okay, but as Sayed, I think, pointed out, in general, that's not always going to be the case. So I would also like to talk about that as well. All right, so first, let me introduce some terminology. So the set of all linear combinations of some given vectors, let's say v1 through vn, is called the span of the given vectors. Okay. So in this picture here that we had, whoops, v, the span of u and v, as we just saw, would be the entire infinite plane. Okay. So the set of all linear combinations, if c and d could be any real number, it gave us the entire plane. Now, however, the span of two vectors will not always be a plane. So looking at the other possibilities that you might see. So there's kind of a trivial case where both of your vectors happen to be zero vectors. So it's a zero vector, it has no length to it, so it's just a point. And in this case, the span of u and v would also just be a point. It would just be the zero vector itself. That's kind of a little bit of a silly case, but I think worth mentioning. Another possibility is that your two vectors lie along the same line. So let's say if U looks like that, and then a V looks like that. In this case, you're not going to form a plane because they lie along this one line. Okay. All right, so in this case, the span would be an infinite line. It's the line that kind of goes through U and V. That's what the span would look like. Okay. So it's only when let's say V is sticking out somehow, sticking out a V, that their span would be a plane. So I've always been drawing it sticking upwards, but I can also stick downwards, for instance. It doesn't really matter. So say a picture like this. In these cases, the span of U and V would still form a plane. All right. Oh, sorry. Okay, now let's take a look at an example which is going to be in 3 dimensions. And it's going to be using some numbers as well. Okay, let's suppose first that we have 2 vectors. These will be vectors in R3. So I'm going to draw them because it's a little bit difficult to draw in 3D. But if I ask you guys what was the span of U and V, would you guys be able to tell me what this is? Any ideas? Sure, so it's going to be a line. So notice that the vector V is 2U. So if even without really drawing it, you can sort of visualize it looks something like this, U and then V. So from that, you can tell that they're just going to span a line. Specifically, it's the line that goes through these 2 vectors, okay? Yeah, in this case, that's all that I'm really checking. So is it a line or like what is it, okay? All right, let's suppose instead I have my vectors U, which is, let's do 1, 2, 1 again. And then let's do V, which is 0, 1, 1. So let's ask the same question. Is the span of these 2 vectors a line or a plane, or what is it? So the span or the set of all linear combinations of them. All right, any ideas what the span of this would be? Sure, so in this case, it's going to be a plane. So we can sort of reason this because we see that u and v are not multiples of each other. So that means they would not lie along the same line. So that means that they would kind of be sticking out a little bit from each other, and they would form a plane. Their span would form a plane. All right, now if I were to throw in a third vector, let's say I throw in w, which is 2, -1, and 3. And now I'm going to ask, what's the span of u, v, and w all together? Any idea on that? All right, so let's go over how we would approach this question. 3D, all right, let's talk about how we would figure this out. Okay, let me, oh geez, how does that work? Oh, okay. I'll have my vectors u and v and w. Yeah, okay. So I think Lixie has the right idea. We already saw that u and v should span a plane. So the picture will look something like this. So what we want to do is figure out, is vector w inside of this plane? If so, then that means it would not contribute like an extra dimension, so that the span of u, v, and w would remain the same plane formed by u and v. That's if w is inside of the plane. Yeah, and then if w is not inside the plane, so otherwise the picture will look something like this. Now here's u, here's v, and then if you can imagine this sticking above the plane, for instance, if it looks something like that. So w is outside the plane. If that's the case, then you could say the span of UVW would be diagonal. And since they're vectors in R3, it would be all of R3 then, okay? All right, but then we still need to determine or ask the question how to determine whether W is in the plane determined by U and V. Yes, all right. So how to determine that? how to determine if it was in the plane spanned by U and V. So the key is to remember that this was the set of all linear combinations of U and V. So what we want to do is determine whether or not the vector W is a linear combination of U and V. That's what we want to determine, okay? So equivalently, we want to know, is W a linear combination of U and V? Because if so, that means it was in the plane. Because the plane was precisely all the linear combinations. And then otherwise, it would not be in the plane, okay? All right, so to determine that, what we can do is take the vector W. Okay. So W, I think it was the vector 2, negative 1, 3. So I want to see if I can set it equal to some combination of U and V. Right. So to check if this is possible, I'm just going to see if I can solve for C and D. So to do that, I can just sort of read off, I have like a system of equations. If I look at the X components of everything, I will get that 2 has to equal 1C plus 0D. Looking at the Y coordinates of everything, I will get that negative 1 has to equal 2C plus D. And then looking at the Z coordinates, we would find that 3 has to equal 1C plus 1D. And then let's just see if we can solve for C and D from these equations. All right, so in the first equation, we have C would have to equal 2. Now, if I go to the second equation and plug in 2 for C, plugging in 2 for C, and then solving for D, we will get negative 5. All right, but then I want to plug these into my last equation to see if they also satisfy the last equation. So if I do 1 times C plus 1D, which was negative 5, I get 3 equals negative 3, which is not correct, not possible. Okay. So what that tells me is that I was not able to find values of C and D which would satisfy all 3 of these equations. So that tells me, therefore, that W is not a combination of U and V. So therefore, it is not in the plane determined by U and V, which was their span. So that means if I add W to this list, it would add an extra dimension to everything. And so the span of UVW would in fact be all of R3 in this example. Okay. So subtraction is taken care of in the case that C or D could be negative. And then we don't really have a multiplication of vectors, or at least one that we would use in this particular context. So you guys maybe talked about the dot product of vectors, which I was going to try and talk a little bit about. You guys have probably encountered the cross product in some of your classes, perhaps, physics, for instance. But none of those products would really help us in this particular problem. We were trying to determine if W was a linear combination of U and V to see if it was inside the plane spanned by U and V. And so a linear combination was something of the form Cu plus dV, and so that's why we're working with that expression. Okay? All right, so any questions about anything that I just did? Any other questions? All right, so I was going to start talking about the dot product, but I see that I don't have too much time remaining for my review. So I think it would be all right if I saved it until next time and we ended a little bit early. So are you guys okay with that? Or would you like me to at least begin talking about the dot product? Okay, so in that case, we'll go ahead and end the review here. In general, this review supposedly lasts until 6:45, all right, just so you guys know.